You're on.
My name is Elena Jackson, and my question is, to what extent does arbuscular mycorrhizal fungi aid plant growth and increase levels of soil salinity? Over these past few months in AP research, I explored the effects of arbuscular mycorrhizal fungi, also known as AMF, on plant growth and varying levels of soil salinity. Before diving into my hypothesis, research, experimentation, and results, I will first give you an overview on salinization and arbuscular mycorrhizal fungi. Soil salinization is an important phenomenon to understand. As the global warming problem progresses in our world today, there have been many detrimental effects on the environment and communities who rely on it for survival. An especially big problem associated with the rising temperatures is soil salinization. As the planet warms, water from the soil is evaporating at a faster rate, raising the concentration of salt in the soil since there is less liquid to dilute it. Great amounts of salt in the soil can upset the nutrient balance of plants or interfere with the intake of vital nutrients, oftentimes leading to the death of the plant. This effect can be brutal on agricultural yields, especially in communities who rely on subsistence farming to support themselves and their families in day-to-day lives. Because of the changes in the climate, global agricultural output has decreased, making food insecurity a real problem. To address these issues on ground soil created by climate change, many researchers have turned to types of fungi that have a symbiotic relationship with plants. One of these being arbuscular mycorrhizal fungi, or AMF. Arbuscular mycorrhizae influences plant makeup, including defense mechanisms and hormone regulation, in turn promoting biomass production. It is one of the symbiotes that can extend a plant's root system, thus increasing its nutrient and water uptake, as well as building its tolerance or resistance to harsh weather conditions, such as drought, extreme temperatures, heavy metals in the soil, or in this case, I will be exploring its effect in increased levels of soil salinity. My initial assumption after narrowing down my question was that the plant fungi systems would be healthier than the regular plant systems as the soil salinity increased. I thought that there would be a drastic difference in plant and root size. I also hypothesized that in the 2 to 5% range of soil salinity, some of the seeds inoculated with AMF would grow, and the seeds that were not introduced to fungi in their respective levels of soil salinity would not sprout at all. The research I had read previous to conducting the experiment led me to believe that AMF allows the plants to withstand more extreme conditions rather than what would usually be tolerable by plants on their own. Now, why is this research important? According to the Saudi Journal of Biological Sciences, for all important crops, average yields are only a fraction, somewhere between 20 and 50% of record yields. These losses are mostly due to drought and high soil salinity, environmental conditions, which will worsen in many regions because of global climate change. The magnitude of this issue is often overlooked, but in reality, as the study goes on to say, salinization is one of the main threats to environmental resources and human health in many countries across the globe. Considering that AMF is known to enhance plant growth and productivity, particularly in environments that induce stress, it could possibly be a solution to prevent agricultural yields from decreasing. This research can bring forth valuable insights on plant fungi systems in different levels of soil salinity to see if it provides a solution to the effects of soil salinity, if it is only a temporary problem or a temporary fix, or if it fails to provide help at all. In the studies I read prior to establishing the question, I noticed that there was very minimal research on the effects of AMF plant relationships in soil salinization. Although it was stated it could possibly build up tolerance, there was not much data on how well it could adapt to those conditions, as well as how much salinization it could survive and continue to grow in. I wanted to explore the effects in different levels of soil salinity to gain a better understanding of the extent to which AMF helps and hopefully produce results that are applicable to agricultural situations in our world today. Next, I will be going through the methodology of my experiment. To start out, I ordered growing containers for the plants, making sure they had holes in them so water could get to the plants and back to the water. I also ordered AMF inoculant that is normally used for farming to gain the best results for my intended goal, as well as ordering Rosette Dwarf Wisconsin fast plant seeds to plant in the soil. I did thorough research on conducting experiments with fungi in soil and found that I needed to sterilize potting soil to make sure the results I observed were not due to other growths in the soil, but were only due to the AMF that I had added in the soil, to make sure it was strictly the AMF. I filled up many 1,000 milliliter beakers with potting soil, covered them with aluminum foil, and taped them up with autoclave tape, and then put them in the autoclave for 50 minutes at 120 degrees Fahrenheit to make sure that there were no growths, to kill off any living organisms that might have previously been living in the potting soil. After that, I used quad wicks, and placed one in every hole of the growing containers to make sure that the plants were getting a consistent water supply. And after I determined the levels that I was going to experiment with, I decided that there were going to be duplicates of each salinity level, one that was inoculated with AMF and one that was not inoculated with AMF, so I could directly compare the results in their respective levels of soil salinity. So the levels I conducted were control, which was no salt added, 0.5%, 1%, 1.5%, 2%, 3%, 4%, and 5%. For the plants with no AMF, I added the soil to the growing chambers, labeled the percentages and that they had no AMF, and placed 2 to 3 seeds of the Wisconsin fast plants in each section. For the plants that had to be introduced to the AMF, I researched how much inoculant to add to the soil and found that I should add about 3.33 grams of inoculant for 1,000 milliliters of potting soil. After I did that, I filled up each of the other 8 growing chambers, labeled them with AMF and the percentages, and placed 2 to 3 seeds in each section like the others. Once they were all ready, I started to water them with their respective levels of salinity. For example, to make the 1% mixture, I added 10 grams of NaCl to 1,000 milliliters of deionized water to make that 1% solution, and then watered the plants and growing chambers that were labeled with the 1% solution. And I did that for all of the respective levels with the correct amounts. I also would like to note that I used gloves as needed throughout the experiment to maintain a sterile work environment. And after I had finished setting up the plants, I placed the containers under growing lights and added water to the containers as needed over the days as I waited for results to show. Now, results. In the first row, I noted how many plants had grown. In both regular and AMF inoculated soil, all 12 plants had grown in the containers for the control group. In the 0.5% soil salinity, 4 plants had sprouted in the regular soil and 9 had sprouted with the AMF. In the 1% soil salinity, 4 plants had sprouted in the regular soil and 6 had sprouted in the AMF soil. In the salt levels 1.5 to 5%, none of the seeds had sprouted, so the soil was the salinity levels were too high to support plant growth. After collecting the numbers of plants, I carefully took samples from each growing container and measured to my best ability the root length and root width of the root systems, averaging out my collected numbers. As you can see in the table, for each level of soil salinity, the plants that were inoculated with AMF consistently have a higher or a bigger average root length and root width than the normal soil plants. Though not shown in the table, I did observe the root systems also underneath a dissecting scope, and the plants that had arbuscular mycorrhizal fungi had a much more extensive root system than their counterparts with the same soil salinity. So you can see that like the AMF really did help root growth in the plants. For my conclusion, I found that arbuscular mycorrhizae does aid plant tolerance to stressors very well. More plants consistently grew for those inoculated with the AMF versus those that were not. They had more extensive root networks, longer and wider roots, and could withstand the soil the salt in the soil more efficiently. This matched with research I had done previous to the experiment, especially from one study I read from Frontiers showing that AMF inoculated plants exhibit significantly higher shoot and root biomass compared to non-inoculated plants. I was surprised to find that the seeds in the 1.5% to 5% range never sprouted, even the ones with AMF. I initially hypothesized that there would be significant differences between the two types, the AMF and the non-inoculated plants, but found that the differences were more subtle than I originally thought in regards to average root measurements. I do believe that there were limitations to my experiments. On the 4% AMF growing container, I found mold growing on the surface, and I think there's a good chance that something could have contaminated the soil in the containers as they were not in the most secure or sterile environment. If I were to experiment again, I would focus on the salinity levels in between the control and 1.5% to try to narrow in on what level the seeds stop sprouting at altogether, as well as maintaining a more sanitary environment to prevent contamination like I saw that might shift the end results. This research is important because it displays how arbuscular mycorrhizae aids plant growth in environments stressed by salinization. There was more growth among the seeds inoculated with AMF, and they had stronger root networks, making it possible for plants to withstand more stress than would a normal plant that was not inoculated. People around the world struggling with agricultural problems due to high salt concentrations can use this research to prevent severe damage to their crop harvest, as well as alleviate pressures on food security and availability. These results offer a partial solution to the problem and can allow more time for researchers and scientists to figure out a more successful solution to salinization and hopefully even climate change, so this problem does not keep spiraling as it is today.
Okay, thank you. How did the choices you made when designing your method impact your research process?
Yeah, so I made choices to research 8 different soil salinity levels, and this choice impacted my research process a lot. I had to sterilize a lot more soil than I originally thought. I actually had to order more seeds because I ran out, and I had to consistently look after the containers to make sure that they were getting enough water and make the salinity solutions again to make sure that they were getting that same amount of water. I also decided to inoculate the seeds right away instead of waiting to add the AMF until after the seeds had sprouted. And this led me to more accurate results in my research because it mimics more of a realistic scenario where AMF would just be added directly right away as people are trying to produce crops.
Okay. How do your findings provide directions for future research in the field?
Yeah, so my findings showed an abrupt stop in growth depending on the level of soil salinity, and I think my findings provide directions to explore more with the different levels of soil salinity to find out at what levels the seed just stop sprouting altogether, and to see if there's a difference between the regular soil seeds that stop at the level at which the regular seeds stop growing and the level at which the AMF seeds stop growing. And then it could also lead to future research on a more permanent solution to salinization, or to see if they could like maybe genetically modify the organism, like the AMF organism, to be even more resistant to environmental stressors.
Okay, thank you. What was the most important research skill you developed as a result of the process, and how might you apply it to your future endeavors?
I think the most important research skill is learning how to adapt quickly to like issues that might arise. In this experiment, it doesn't always pan out the way you intended, and when something doesn't work, it's good to be able to think fast and come up with an alternate way to accomplish what you originally wanted to accomplish. For example, I sterilized more soil than I thought I needed, so when I accidentally had mixed AMF with like the soil, which I was not supposed to, I could easily adapt to that situation and use my excess soil to fix that problem instead of having to wait a long time to sterilize more soil.
Okay, thank you.